Okay, so we're going to start the second session of this afternoon. We're very happy to have Chi-Ming Chang from Tsinghua University, who will tell us about black holes from supercharge cohomology. Let's thank him.
Okay, so first I would like to thank the organizers, especially Professor Yao, for holding this wonderful conference and inviting me to speak here. And today I will tell you a cohomology problem that's called supercharge cohomology and how it gives us non-trivial information about black holes. And this talk is based on these several papers I have with my collaborators, and also see these 3 papers by people in Korea and these 2 papers by people in PI and Boston. So first, we all know that black holes are singular solutions in general relativity, and usually it's believed that the resolution of this singularity requires quantum mechanics. And we've also learned from the talk by Professor Witten last week that black holes satisfy the law of thermodynamics, and especially it has entropy, and that is proportional to the area divided by 4G Newton. And a very important central dogma when we used to study black hole is that if we look at black hole from the outside, a black hole can be described in terms of a quantum system of microstates. And these microstates will evolve unitary under time evolution. And the previous entropy given by the area divided by 4G Newton, actually, if we take exponential of this entropy, is the number of these microstates. So the black hole entropy has a macroscopic statistical mechanism interpretation as the number of states. And so the central dogma, we can put it in a more precise framework that is under the ADS-CFT correspondence. So this is a duality between quantum gravity in ADS space and conformal field theory on the conformal boundary of ADS. And now, if we consider black hole in this ADS background, and it is due to a thermal density matrix that is a sum with this Boltzmann factor over the microstates. So this Ni, I use them to denote the microstates. And now if we just use very standard statistical mechanics formula, consider trace law log law, and that gives us the entropy, and entropy is given by area divided by 4G Newton. We know that the ADS-CFT is a non-perturbatively complete framework of quantum gravity. So given this very powerful framework, we should be able to answer more refined questions, not just counting the number of states. And one question I would like to propose is that we want to ask that what are the black hole microstates? We do not just want to know the number of them, we want to know more about what are them. And let me try to make this question more specific. So now let's take a particular state in this song. So a black hole is due to a density matrix, and we pick a pure state in this density matrix. And I would like to ask the question, what's the bulk dual of this pure state? And more specifically, how many of these states admit a pure gravity description? And so you may think that some of them may not be able to describe using pure gravity. You may need to use string theory to describe them. And I would like to know like, how many of them I can describe them purely using gravity, the IR effective gravity theory. And because these states are pure states, so the bulk dual should actually be nice and should be free of any singularity. And also because it has no singularity, so we also expect that it should has no horizon. And you can understand in a different way is that because if you have horizon, it should give you some area, and the area means that the area is the area give you entropy, and entropy means that you have multiple states, not just single state. But now if I take just a single state, then the horizon area should be 0, so actually it should be horizonless. And you also want it to be well-defined, so it should also be smooth. So no singularity and no horizon. Right. So the question is, how many of these admit a smooth and horizonless geometric description? So that's the thing I would like to explore. Yeah, good. So now, so even if I specify this question a little bit, it's still very hard to answer. So to answer it, let me consider a slightly more special case. So in this talk, I will focus on the BPS black holes in ADS5, and they are macroscopic. So their horizon size, their horizon radius is of the same order as the ADS radius. And these black holes on the ADS CFD correspondence, their microstates are due to BPS states in the N equals 4 super-Young mills. And in this talk, I will also use the state operator correspondence in CFT and talk about the BPS operator. So I would actually use BPS state or BPS operator, these two terms interchangeably. And so about this correspondence, the counting part the counting of the microstate part has already been understood. So in this case, on the box side, we can see that if we compute the area divided for G Newton, and this entropy scaled like n squared. This n is the rank of this the gauge theory, and if now we can actually interpret this as log of the number of states, and this log of number of states was reproduced by the superconformal index from the CFD side. The superconformal index is a state counting with -1 to the fermion number. So the counting part of the problem has been already solved. So now we turn to the next question is ask, what are these black hole microstates? And the main tool that I will use in my talk to answer this question is something called supercharge cohomology. I will introduce it later. And the supercharge cohomology contains new information beyond the superconformal index that was used to count the state. So first, the supercharge cohomology contains a complete BPS spectrum information, and it can count the BPS state without the -1 to the F. So it's an absolute counting. There's no cancellation between the number of fermion and number of bosons. But furthermore, it contains the information of the wave function of these BPS states, modulo the exact term in the cohomology. And so using this wave function information of a BPS state, we can actually talk about BPS states and try to relate BPS states at a different rank n. And this n under ADS CFT correspondence correspond to the Borg gravitational coupling. So we can know how this BPS state changes if we try to increase or decrease the Borg gravitational coupling. And using this information, we can try to answer the question, what are the black hole microstates? So, sure.
I think most of the black states, yes.
There could be some. Okay, first, they are in a larger limit. They are relatively few comparing to most of the state that you can see from index. Because from the index, we've already seen the black hole entropy growth. So, so those states are actually not that important when you study black holes because there are relatively few of them. Okay. So the first new information is actually not very important. The important thing is this second one, that we know some partial information of the wave function of these BPS states. Good. Right, because for an index, you've already see the square root. That might be important, but we haven't studied that. Good. Okay, so let me tell you some of the results that we have. before just going to the detail. So first, we have the classification of the supercharge cohomology, and we also propose the conjectural bulk duals. And we classify the cohomology into two different categories. I mean, this is the not very refined classification. We only classify them into these two categories. The first one is called monotone cohomology, or also some other people call them graviton cohomology. And their conjectural bulk dual are smooth and horizonless geometries in the bulk. And the second category of the cohomology are called the fortuitous cohomology, or people also call them black hole cohomology. And that is because their conjectural bulk dual are typical black hole microstates. So this is the outline of my talk. So first I will give you the definition of supercharge cohomology, and then I will talk about the classification of it, and then talk about the bulk dual of supercharge cohomology. And in this talk, I will mainly focus on the N=4 super Young Mills. But finally, if I have time, I will also tell you some result about the D1, D5 system. Okay. So first, supercharge cohomology can be defined very generally. It only needs a supercharge Q, and that is nilpotent, Q squared equals 0. But in this talk, as I mentioned, that we focus on N=4 super Young Mills with SUN gauge group. And in this theory, we have 16 supercharge Q and 16 conformal supercharge S. And we can pick a pair of them, 1Q and 1S. And in radial quantization, S is just the Hermitian conjugate of Q. And now using Q and Q dagger, we can compute the anti-commutator, and this will give us a bosonic charge. I call it delta. And more specifically, it is a linear combination of the energy of the BPS state and 2 angular momenta and 3 R charges, Q1, Q2, Q3. And the BPS states are the states that saturate this BPS bond. That means delta equals 0. And because Q is nilpotent, we can define this Q cohomology. That is, we first take the Q closed operator, the space of Q closed operator, and mod out by the space of Q exact operators. And this Q cohomology is the supercharge cohomology I talked about. And now we can just use a very simple Hodge theory argument that will give us a one-to-one correspondence between Q cohomology classes and BPS states. And this one-to-one correspondence is the same one-to-one correspondence of the one between Dirac cohomology classes and harmonic forms. And so from this definition, we can immediately see that the superconformal index is just the Euler character of this supercharge cohomology. And we also know that from various arguments that the superconformal index is protected by supersymmetry. So that means it does not depend on for example, the Young-Mills coupling G Young-Mills. But actually, in many cases, the cohomology itself is protected. For example, in the 1D SUSY sigma model. But for higher dimension, it's less clear that whether the cohomology itself is protected. But there is a non-renormalization conjecture stating that this Q cohomology is independent of the Young-Mills coupling G Young-Mills, as long as G Young-Mills is not 0. And it is known that if we compute the Q cohomology at G Young-Mills exactly equals 0, and slightly away from 0, you will see a jump of the cohomology. But as long as you are away from G Young-Mills equals 0, the conjecture is that the cohomology will stay invariant. And there are several evidence for this conjecture. So first, we can try to match the BPS spectrum at the infinite rank case. And I will talk about this evidence later. And there's a second evidence is that we can consider the consistency between this non-renormalization conjecture and the S-duality of N=4 super Young-Mills. So this part is a pure field theoretical evidence, but I will not talk about this in this talk. And now we will just assume this conjecture that Q cohomology is invariant under geometries as long as its geometry is non-zero, and then work at weak coupling. So geometry is much smaller than 0. And then we, from the box side, we need to actually consider strong coupling, the strong top coupling case. But we will just, from the field theory computation, we will just work, do a weak coupling computation. Yeah.
A set of operations.
Right, right. I consider all that is Q close and model by the space of all that is QZ. Yes, depends on Q, and I pick a Q in angle sports. Yeah. Good. Does not apply. It's already known that there's a jump. The cohomology will jump if you are at G equals 0 and G non-zero. Yeah, it's a free theory. Yeah. Good. Yeah, once you infinitesimally deform away from G equals 0, and it's expected that the cohomology will remain invariant if you turn even larger geometries. Good. Okay. So we will work at weak coupling, and at weak coupling, local operators can be written in terms of multi-traces of fundamental fields with covariant derivatives. And both fundamental fields and covariant derivatives, they are n by n matrices, but we need to map out by taking into account the trace relations. So these trace relations actually play a very important role in the study of supercharge cohomology. So let me give a very simple example of the trace relations. Consider any 2 by 2 matrix X, and this following relation it always holds. And this relation is what I call a trace relation. And so now, for just a single type of matrix X, it's actually very easy to write down all the trace relation. But if you consider many different types of matrices, they can also be Poissonian or fermionic, to enumerate all the trace relation is actually very hard. But that would be our case because we have many different types of fundamental fields and covariant derivatives. But in this talk, I will only use a very simple property of trace relation. That is, let me denote IN to be the space of all trace relation for n by n matrices. And it's obviously true that IN plus 1 is a strict subset of IN. You always have fewer and fewer trace relation if you consider a larger and larger matrix. Okay, and also at weak coupling, it suffices to work with fundamental fields that are BPS in free theory. And we can actually assemble these fundamental fields that are BPS in free theory into a superfield. I would denote it by this capital psi. It depends on two bosonic coordinates z alpha, and this alpha can be plus and minus, and the three fermionic coordinates theta I can be 1, 2, 3. And now if we expand this superfield in terms of z and theta, these coefficients are the fundamental fields and also covariant derivative acting on fundamental fields. For example, this lambda alpha is the gauge node in angle sports polynomials, and this theta I are three complex scalars, and psi I are three complex fermions. This F++ is a particular self-dual, a particular component of the self-dual field strength. And there are other higher terms in this expansion. There are a covariant derivative acting on these fundamental fields. And one advantage of assemble these BPS letters into a superfield is that the supercharge action take a very simple form. Q acting on psi just give us a psi square. And also this supercharge action satisfies the Leibniz rule. So Q acting on A times B equals Q acting on A times B plus or minus A times Q acting on B. Whether we have plus or minus depends on whether A is Poissonian or fermionic. Good. Now let's come to the classification of the cohomology. Let me introduce a bit few notation and then we can discuss the classification. So let's define this H infinity, that's the space of formal multitraces without imposing any trace relations. So we just have a bunch of a trace of this psi and some derivative acting on psi and product of these traces. And this Hn means that the space of local operators in SUN theory. That means we have these multitraces, but imposing the trace relation at rank n. So the space without imposing any trace relations, you can also understand that as the space of local operator in the infinite rank theory. Because if you consider infinite rank matrices, there are no trace relations between any multitraces. And now this In we've already defined before. This is a space of trace relations at rank n. And this Hn is just, you can take H infinity and quotient out the trace relations In, that give you Hn. And this quotient relation can also be very simply written as a short exact sequence. We have inclusion map that embed the trace relations into the space of multitraces. And we also have this quotient map that basically just impose the trace relations. Now we can take the cohomology on this short exact sequence and get the long exact sequence. So we have the induced inclusion map, quotient map, and also this new map, delta. And this sequence is exact. That means image of I is the kernel of pi, and image of pi is the kernel of delta. And this N is just a cohomological gradient that basically just give you the number of superfield psi. Because from the previous this relation, Q acting on psi give you psi squared. You know that psi and Q, Q increase a number of psi, so you can use the number of psi to grade the cohomology. And now, so this one is the thing that we are interested in, the cohomology of this Hn, the space of local operators in the rank n theory. And this space, we can basically split that into two parts. The first part is given by the image of pi. So that part you can understand as the cohomology classes coming from infinite rank theory. But one important thing is that not all cohomology classes are coming from infinite rank. There are also some other cohomology classes that only exist at finite rank. They are not coming from infinite rank. They are given by the image of delta. So this first category, we call them monotone, and later we will see that they are related to gravitons in the ADS dual, the bulk dual. And the second type of cohomology, we call it fortuitous cohomology, and later I will tell you how they are related to black hole microstates. Okay, and this delta, this image of delta, from this short exact sequence, you can also see that it's given by, I take the space of all cohomologies and quotient out by the image of pi, that's the monotone cohomology. I quotient out the part, the monotone part, and then that's what we call the fortuitous cohomology. So these are the formal definition, but next let me discuss some properties of the monotone and the fortuitous cohomology. And these properties are important properties. I will use them later, and we can infer the gravity duals from these properties. So let's consider this O is a representative of a Q cohomology class. And we can actually write O non-uniquely as a multitrace O tilde. This means that if we have two multitrace, say O tilde 2, they are related by a trace relation, and then they will give you the same operator O. And so if O represents a monotone cohomology, that means a Q acting on O tilde actually gives you 0 without using any trace relation. And since O tilde, to write down the multi-trace, we do not need to specify what's the rank we are working with. So that actually means that O tilde will give us a sequence of cohomology classes at higher and higher rank. And now we also use the one-to-one correspondence between cohomology class and the BPS state. So that would tell me that O tilde will give us an infinite sequence of BPS operator at increasing rank n. So here the y-axis is the delta. So recall that for BPS state, delta must equal to 0. So we have this infinite sequence of BPS operators. And now let's turn to the fortuitous cohomology. So if O represents a fortuitous cohomology, that means Q acting on O tilde will actually give you a non-trivial trace relation. So that if we further impose the rank n trace relation, then I would have Q acting on O equals 0. So that means Q would represent the cohomology. But from the property of trace relation, we also know that there are fewer and fewer trace relations if we consider higher and higher rank. So this particular trace relation may not be a trace relation if we increase the rank n. So there should exist some rank, I call it n star, such that if the rank if n is greater than n star, then Q acting on O tilde is not a trace relation. But if n is less than n star, then Q acting on O tilde is a trace relation. So that means O is only Q close when the rank is smaller than n star. But O is not a Q close operator when n is greater than n star. So we have this situation. So we only have a finite range of, we only have a Q cohomology or BPS state at a finite range of n, of rank n. So there are these red stars denotes. So these red stars are denotes the Q cohomologies at some smaller ranks, and they have 0 delta. But now if we try to increase n to this range, so we will no longer have Q cohomology. So this O tilde will actually give us some non-BPS operator. And this non-BPS operator should have non-zero delta, and it should satisfy BPS bound, so they should have positive delta. So we have this schematic plot here. Okay, any questions? For the particular one I will show later, the n star equals 2. Yeah. Right, so far there's no, there are more examples of, there's one particular fortuitous cohomology that people study most, and for that one we know that n star equals 2, but there are some other fortuitous cohomology classes people know of, but they haven't studied them well enough to tell what's the n star. But here, so let me mention this point a bit more. So for the monotone cohomology, they admit infinite n limit with a fixed O tilde. But for fortuitous cohomology, there's no infinite n limit with a fixed O tilde. And I should stress that this particular infinite n limit I'm talking about is actually not the larger limit that usually we take to study black hole. In that case, because in that case, usually we consider the energy scale like n squared. But if we fix the form of O tilde, then we fix the energy. So in this case, we consider fixed E, but taking larger. Even though this is not the usual larger limit, we study black hole, but I will show you that this particular limit is also very important to understand black hole. Okay, now let me talk about examples monotone and fortuitous cohomology. And first, about the monotone cohomology. And so in Engels-Force binomials, we need to consider, to write them down, we need to consider one forms on this superspace. And this superspace has basis dz and d theta. So we have this d psi that can be expanded in this form. And now the previous Q action on psi can be written like this. We have Q acting on d psi just is just equals to the commutator of psi and d psi. And now from this Q action, it's very easy to see that the multi-trace of d psi, they are Q closed and not Q exact without using any trace relation. And in fact, if we consider the infinite rank case, that means without using any trace relation, all the cohomology classes are represented by these multi-traces of d psi. And now if we consider finite rank n, and there are some theorems that would tell us that all the monotone Q cohomologies are obtained by imposing trace relation at finite n on these multi-traces of d psi. So actually for the n equals 4 superyoung we know all the monotone cohomologies. And so let me add one more comment. So the space of monotone cohomologies is actually very large, even though they can be written very simply down like this. So first, all BPS operators in n equals 4 superyoung they are called 116 BPS. Of course, they contains all the monotone BPS operators because, I mean, all BPS contains both monotone and fortuitous. Now we restrict to the smaller subset. But the important thing is that the space of monotone operators contains all the 8 BPS operators. So it's actually a very large space. Okay. Now let's turn to the fortuitous cohomology. And like the monotone cohomology, we do not have a formula for all the fortuitous cohomology, but by a brute force comprehensive search in the SU2 theory, up to high spin and R charges, we found the first fortuitous Q cohomology. I have to comment on this. So first, this is it's very hard to find it. And in total, we've constructed 10 to the 5 cohomology classes. All of them are monotone, except one is fortuitous. But this actually doesn't mean that fortuitous are few in general. We will see later that if we consider even higher spin and R charges and also higher ranks, the fortuitous cohomology there are much more fortuitous cohomology than the monotone ones. And shortly after our paper, a group in Korea, they found a very simple and explicit representative of this fortuitous cohomology. It takes this form, and it is constructed out of some theta derivatives on the superfield side. And you can see that in order to write it down, we only need the theta derivatives and no z derivative. And this actually defines a very interesting sector of the operators, and that is called the BMN sector. And working within this BMN sector, people in Korea, they perform a more efficient search and achieve this following result. First, they consider SU2 and SU3 theories, and they found multiple infinite towers of fortuitous cohomologies. And if you consider, they also consider SU4 theory, and they found the leading fortuitous cohomology. And this is the state of the art right now. Yes, this is related. Because if you do not consider any z derivatives, so z derivative basically means you consider some infinitesimal translation on R4, and if you do not have any of them, you can try to reduce that to actual quantum mechanics, then that's the BMN quantum mechanics. Okay, good. So even in this very restricted subsector, people only have very limited results because finding them is actually a very hard problem. But now let me talk about their bulk duals. And first, let me specify what kind of bulk dual that we are searching for. So first, we know that by the non-renormalization conjecture, supercharge cohomology is independent of top coupling, lambda, because it's independent of G-Young mules. And but we will actually focus on large lambda. And that's the place the bulk theory is, the bulk theory is a supergravity. And we will look for bulk duals in the IR supergravity. And first, let's start with the monotone cohomology. And we also first consider, for simplicity, we consider the infinite rank case. And the conjecture is that in this case, they are due to BPS motif gravitons in APS 5 times S5. And for this conjecture, we have a very strong evidence for it. So the evidence is coming from counting. And so we can count how many multi-traces we have that are made out of this side. And this counting exactly matches with the BPS multi-graviton partition function in the bulk. So from this evidence, we are quite confident that the conjecture is true. And now we can try to consider finite N. So, but we would like to use the information that we have at infinite N, and then we can try to infer what the bulk dual of the monotone cohomology at finite N. So we are looking for bulk objects that reduce to BPS gravitons in the bulk gravitational coupling goes to 0 limit, because that's the N goes to infinity limit. And now, before proposing the bulk dual, let's discuss the intuition that we have for this bulk dual. So because the bulk BPS gravitons in ADS, they are actually solutions to the linearized supergravity equation. And if we consider infinite rank N, that means we have very weak coupling. So the supergravity equation becomes linearized. And this bulk gravitons, the bulk BPS gravitons are solution to this linearized equation. And now if we try to increase the bulk coupling, and that means the originally linearized equations will become nonlinear. And for the monotone cohomology, we know that we can actually, starting from infinite rank and then slightly reduce N. So we will expect that these BPS graviton solution will gradually become nonlinear solutions to this nonlinear supergravity equation. And such solution should be smooth and horizonless, meaning that they should be non-singular if we just gradually increase the bulk coupling. So this intuition led us to propose the following conjecture, that is the monotone Q cohomology at finite N, they are due to quantization of the smooth and horizonless geometries. And there are two evidence for this conjecture. First, as I said, that all 1A BPS operators are monotone, so we can actually consider a particular sector of 1A BPS operators, and it's known that they are due to generalizations of the Lin-Luni-Madasena geometries, and these geometries are smooth and horizonless BPS geometries. And this correspondence is so far only a classical correspondence between 1A BPS operators and 1A BPS geometry. But for the 1/2 BPS operators, this classical relation can be made fully quantum. So that is given by that if we consider original Lin-Luni-Madasena geometries, they are 1/2 BPS. We can actually consider a quantization of this geometry, and this quantization will actually reproduce as the partition function of the 1A BPS operators. Let me discuss a bit more about this quantization of the Lin-Luni-Madasena geometry. So first, on the CFT side, we are focusing on half BPS operator, and these half BPS operators are constructed out of the multi-traces of a single scalar x, that is one of the previous 3 scalar phi. And if we consider finite N, this multi-trace form of x, there are trace relations among different multi-trace form of x. So there are exact so I mean, if we consider trace x to the n plus some integer, positive integer m, then for each m, this single trace can be, under the trace relation, can be rewritten as multi-traces. And these are all the trace relations that we have. And also, in this case, it's actually very easy to solve the Q cohomology because Q just simply annihilate X. So Q will actually annihilate all these multi-traces of X. That also means that all the near-BPS operators are monotone. So we can very easily compute the near-BPS partition function. The first bracket, that is just the contribution of the multi-traces of X without imposing any trace relation. And this second bracket, you can see that we have something in the numerator. That means we cancel out some of these things in the denominator. That means we impose the trace relation. Okay? And now we would like to consider the box side. We would like to recover this partition function from the bulk computation. So let's see. Let me go a bit faster. So the Lee-Looney-Malasena geometry has a classical space of solutions that can be parameterized by the Z2 value functions on R2. And that function can be represented by this kind of black and white figure on R2. The black region will correspond to u equals 1, and white region correspond to the Z2 value function u equals 0. And the total area of this plot is given by the total flight form flux on S5. And we also have the formula of the ADM mass of this geometry. And there's one more thing is that this M is equipped with a symplectic form that can be determined by type 2B supergravity. And so the symplectic form has been explicitly worked out in the infinite n limit case. That is by using something called the small fluctuation approximation. That is, we consider a very big black disk near the center, and there could be some small fluctuation on the boundary of this disk. And using this symplectic form, and we can quantize the system and then get this partition function. You can see that this one agree with the previous one in the infinite n case. So if we take infinite n limit, the trace relation would just completely drop out and we get the first term. But we're actually not satisfied with this. We can actually compute the symplectic form at finite rank. And I will actually skip the argument, but so that's the result of the symplectic form. And now, to quantize the system, we just need to find a quantum system whose commutator reduced to this symplectic form as the Planck constant to 0 limit. And such a quantum system is actually a free fermion system. And using this free fermion, we can compute the partition function of this free fermion. And that, so this is a result. You can see that this is exactly agree with the CFT partition function. See. The CFT one here, you can actually cancel so these two factors. And if I cancel this part, the infinite product will become the finite product from 1 to n, and that agree with the formula we have from the bulk quantization. Okay, so first, this result is actually quite surprising. That is because from the bulk side, the thing we are doing is semi-classical quantization on the bulk supergravity solution. And usually we would think that only hold at the large n limit. But the result we found actually agree with the CFT answer, even at finite n. And there are some generalization that one can do. We can consider similar quantization for the 1/4 and the 1/8 BPS geometry, and then try to compare the partition function from this quantization with the CFT partition function. And that will give us more evidence on the conjecture that monotone cohomology are due to smooth and horizonless geometries. That part, I'm not sure. So for the 1/4 and 1/8 BPS geometries, they are much more complicated. And it could be that we can only carry out the quantization in a larger limit. Yeah. And now let's come to the bulk duals of the fortuitous cohomologies. And they are the more interesting things. And first, we actually do not know much about their bulk dual, but we know a couple of things. One thing we know is that there are exponentially more fortuitous cohomologies than monotone ones. And this property can be made into the slogan that is a typical black hole microstate is fortuitous. Let me try to argue this. And that is coming from a bound on the number of monotone Q cohomologies. So let's first start with the number of monotone cohomologies at finite n. And then, of course, this number is smaller than the number of monotone cohomologies at infinite n. That is because if we impose a trace relation for the infinite n monotone cohomology, we get the finite n monotone cohomology. So we have this inequality. And then by our previous conjecture, this number is equal to the number of BPS multi-graviton states in the bulk. And of course, this number is smaller than the number of all particle states in the bulk, all multi-particle states in the bulk. And we can estimate this number by knowing that the entropy of a gas or free particle will scale like energy to the 9/10. So the number of all multi-particle states should scale like e to the energy to the 9/10. And if we are interested in black holes, we can just simply substitute the energy equals to the rank n squared, and that will give us e to the n to the 9/5. On the other hand, we also know the growth of the total number of BPS states. And the total number of BPS states is equal to the sum of number of monotone and the fortuitous. And that from the superconformal index, we know that that will scale like e to the n squared. And we can see that e to the n squared is much larger than e to the n to the 9/5. So that tells us the number of fortuitous operators should be much larger than the number of monotone ones. And hence, a typical black hole microstate is fortuitous. But I mean, we do not actually just want to know the number of them. We also want to have at least some knowledge about what are these fortuitous BPS operator. And again, we can try to know what they are by consider the large n limit, and that is the weak gravitational coupling limit. And from our previous discussion here, we see that if we take some fortuitous BPS state and take a larger limit, at some point, at some particular n star, they will become non-BPS. And in particular, if we take the fortuitous cohomology that has been explicitly found for n equals 2, if we try to take the large n limit, it actually becomes, I mean, from this form, we can read off the bulk dual. I mean, it becomes a non-BPS operator, and it is actually a product of these three vectors. The first vector is actually correspond to a bulk graviton state, and the second vector is also correspond to a bulk graviton state. And the third vector is not Q-close, so that makes the entire thing non-BPS. And in the larger limit, this single trace corresponds to a single massive string state. And now, if we try to extrapolate this to finite n, we would propose that the fortuitous cohomology at finite n should correspond to some string and d branes. The bulk dual should involve strings and may also involve d branes, and generally on some supergravity background. Another way to understand it is that because the bulk dual should also have the property that at a very weak coupling, the bulk duo is non-BPS, but if we increase the gravitational coupling, it becomes BPS. And it's actually very hard to imagine any supergravity solution can have this property, that at very weak coupling, it's BPS, but when we increase the gravitational coupling, it becomes, at weak coupling, it's non-BPS, but when we increase gravitational coupling, it becomes BPS. So that led us to propose this conjecture, that the fortuitous states correspond to string N or D branes on supergravity background. And so let me stress once again here that we are working at large Topf coupling, such that the bulk duo has a semi-classical supergravity theory. I mean, the bulk duo has a low energy supergravity theory. And so this proposal is actually different from the standard Strominger-Vafa paradigm that describe black holes as that describe black hole microstate as D branes at weak Topf coupling. So because our proposal is as strong Topf coupling, so it's different from the standard Strominger-Vafa one. Okay, so time. So first, there are a different range of the Topf coupling, and you can try to take the Strominger-Vafa answer and try to increase the Topf coupling, but it's not guaranteed that there are no any funny thing going on. So the brane configuration in these two sides may be very different. Yeah, that may be possible, but I would think that should be very hard. Yeah.
And they come in this black for like states of this happen. I think that is assumption is that once you turn on from invasive, there's no the biggest.
Yeah. So in the standard Strominger-Vafa paradigm, they just said that a strong Topf coupling, you have some black hole microstates, but you do not know what are these black hole microstates. And yeah, you know the number, but for example, you do not know you do not know what's their wave function. How do you describe them in string theory? Can they be described using just pure supergravity, or you need string and branes to describe them? And right now, my proposal is that the majority of these black hole microstates, you cannot describe them using pure supergravity. You actually need to have string and branes in order to describe them. Even though at strong Topf coupling, at low energy, the low energy effective theory is supergravity. But in order to describe this black hole microstate, you cannot stay in the low energy supergravity. Good. Okay. So because the lack of time, let me skip the part about D1, D5. And just mention that at D1, D5, there's actually very similar story. So in D1, D5, there's a very large class of smooth and horizonless geometry, and you can count, and they are called superstrata. You can count the number of them, and this number is bounded by the number of multi-gravitons in the bulk. And we also know that the number of multi-gravitons is much smaller than the number of black hole microstates. So in D1, D5, this number is like the number of monotone operators and infinite n, and this number is the number of fortuitous operators. Okay, good. So let me conclude. And in this talk, I talk about the ATS CFD dictionary of supercharge cohomology, and we have this classification of cohomology as monotone, or also called graviton cohomology, and fortuitous, or also called black hole cohomology. And the bulk duo or monotone cohomologies are smooth and horizonless geometries. And for fortuitous cohomologies, should corresponds to typical black hole microstates. And we have explicit formulas for all monotone cohomologies in n equals 4 superYAMLs. But for the fortuitous cohomologies, we only know examples of them for the rank equals 2, 3, and 4. And of course, we would like to construct fortuitous cohomology at larger n, and they are key to understand black hole microstates. And I will actually, it may at first seems hopeless to construct fortuitous cohomology at larger n because only to construct them up to n equals 4 is already very hard. But I would try to argue that maybe it's enough to go to n slightly equal to 6. And if we can construct the fortuitous cohomology for n roughly equals 6 or higher, we may already start learning some non-trivial feature about black hole microstates. That is, this intuition is coming from consider a ratio between the entropy and the n squared computed from the superconformal index at increasing n. And this ratio, if we consider infinite n limit, that will approaches the one given by the Beck-Hawking entropy formula. But if we consider finite n case, we can actually already see that this number converges to its infinite n value at roughly n equals 6. And so besides the study in n equals 4 superYAMLs, we can consider generalizations. For example, consider supercharge cohomology in the D1, D5 CFT, in 4D n equals 2 CFT, and also we can also study them in the BMN matrix quantum mechanics. And let me mention a bit more on this final case. So, in this case, the CFT, the field theory side is in particular simple because it is just a quantum mechanics, and there are also very interesting bulk dual that we can study. We can actually, the BPS states in the BMN quantum mechanics, they are due to the black hole microstates of black holes in M theory on the PP wave background. And we can actually count how many BPS states in the BMN quantum mechanics. And by computing the Witter index, and it has been shown that the Witter index exhibits a black hole entropy growth. So that actually predict the existence of these BPS black holes. And they should be very interesting to study them. Okay, let me conclude here. Thank you very much.
Now we have time for questions.
Quantum geometry has take a larger limit. It becomes classical geometry. So you have this quantum geometry for this, yes.
If you I think the question you're asking is about the half BPS1. In this case, we can quantize the geometry, and if you take larger limit, they actually do not become classical. They becomes these multi-graviton states, so they are still quantum.
Does Chi-graviton expansion provide a good organization principle for these trace relations? Because I think you were referring.
Yes. Right. So the question is about for this partition function, we can consider we can rearrange it into some expansion form that's called giant graviton expansion, and that particular expansion form has some bulk meaning as giant gravitons in the bulk. But as far as I know, this particular giant graviton expansion actually does not give us so far hasn't been giving us useful information about trace relations. And usually you need to first know about the trace relations, and then you can try to interpret, you can try to give physical interpretation of this giant graviton expansion.
Any more questions? Okay, if there are no more questions, let's thank Chi-Ming again.